Okay, let's get started.
Yeah.
So, today I will be actually speaking of unsupervised learning, but I'll give you just a very brief recap of a couple of main ideas of supervised learning. So, the other day we discussed a bit an introduction of what machine learning is. We are saying that machine learning is a collection of algorithms and techniques that allows us to design systems that can learn from experience. We identified two main areas within machine learning. We said there is supervised learning, which we talked about last time. Supervised learning focuses on learning functions, basically. So in supervised learning, you're given a set of pairs of inputs and outputs, and you're asked to learn to predict the output given the input. There's a super called supervised because you're given the right answer to when every time you try to perform your action, you try to predict something, you're given the right answer and you're given a chance to adapt your behavior based on this supervision signal you're given. Today we will speak of something different, which is unsupervised learning. In this case, the experience you're provided is just a stream of multidimensional data. So this data, which is encoded as vectors, may represent many different things. So you could have a stream of images, of speech, of audio, different type of data, different type of signal. And in unsupervised learning, you are asked to extract some information, some structure from this data. So you're not given an answer, you're not given a task of predicting something, you're just given the task of understanding somehow your data. And this might seem a rather general problem, and indeed there are many subfields within unsupervised learning which deal with different types of structure which are interested within your data. So before going into this, I would just to recall a couple of ideas of supervised learning. And one of the main points we stated was that when you're given your data, your set of input and outputs pairs, you don't want to just learn these pairs. You don't want to memorize them. You want to learn some relation which will be useful to predict the output if you're given new inputs, which you have never seen before. So in supervised learning, you are asked to learn something which generalizes over your data to new data. And one of the topics we spoke about was how to evaluate how good your system, your supervised learning system is, based on exactly this principle. So we spoke about a thing called holdout, which requires you to split your data, learn your model on a subset of your data, and try to understand and to evaluate how good the model which you learn on one part of the data it is when you apply it to predict the output in the second part of data you have never seen before. We have spoken of more sophisticated way of doing this, for example, cross-validation. And we said that one important problem within supervised learning is overfitting. So overfitting is the phenomenon that occurs when your model becomes very good on the data you are trained on, so you are basically memorizing your data, and but then fails to generalize to new data. And we spoke about how you can try to avoid this. Today we will focus on this separate task, which is unsupervised learning, but we will say something on how this can actually help us to perform better on the previous task, which we spoke last time. So, as we said, unsupervised learning, you are provided a stream of data, which may come from the most different sources, and you want to find some structure. There are two main types of unsupervised learning we'll see today, which are clustering and feature extraction. In the case of clustering, the type of structure you want to find is you want to find subgroups, subparts of your data. So you want to group your data into clusters or families of related data which shares important features. This is a task on its own because it has a lot of practical applications. While feature extraction is the second subfield we will describe today, which aims at finding better representations of your data. So you're given your data, which may be an image, and is given as basically a vector. For example, in the case of an image, you will be given a vector where each element represents the value of a pixel in a different point into the image. When you do feature extraction, you will try to extract from this vector a new representation, so a new vector which is computed from the previous vector, but which might be smaller and might be more informative. So what we will try to do is to retain all the relevant information and represent it with fewer element, so a shorter vector, because this allows us on one side to compress the data. So this is an aim on its own. If you can represent all your information using a shorter vector, this means that you will compress the amount of memory you need. But more importantly, finding a better representation, a more compact representation that preserves all the information you need is actually an important pre-processing step if you want to do supervised learning. So all your models, if you are able to do some good feature extraction at the beginning, will usually perform better, will be less prone to overfitting, and will exhibit some nice properties. So clustering. As we said, clustering is the problem of finding groups, subgroups into your data. This has many practical applications. One example I would like to make is customer segmentation. So in marketing, you might have a lot of data, which represents your users, your customers, and you might be interested in finding if there are segments, clusters, and subsets of your users which share some characteristics. For example, they might respond better to a certain type of ad or to a certain form of communication to them. And if you are able to identify these subgroups in your data, you can target your communication and your advertisement in the best way and hopefully have better results. One key property of one key factor when you do clustering is that you must define what does it mean to share properties. I mean, you want to define some subgroups which are similar in some sense, but similar can mean many different things. So depending on the kind of similarity measure you will define, you will get different clustering algorithms, which will be more or less suitable depending on the domain you're interested in. So a bit like in supervised learning, again, there is not a single algorithm which is the best clustering algorithm which you can use every time. You need to understand for each algorithm what is he actually doing, what is the type of similarity he's looking for, because then you can apply it in the kind of domain which is more suitable for that specific algorithm. So the first simple algorithm we will talk to is k-means. So k-means tries to attempt at identifying the cluster in a very simple and intuitive way. It takes us parameter, which is a parameter which you must set yourself, and we will discuss how you can set it, the number of clusters you want to look for. So you might say, okay, I would like to identify 3 relevant groups within my data. Then the data, for each of these clusters, you take one of the data points as initial value of the center of this cluster. And you assign to each of the clusters all data points which are more similar to the center of the clusters, more close in terms of means of squared distance between the two vectors to the center of the cluster. And you try to find the assignment of the centers and the assignment of data points to these clusters, which minimizes this objective function. So you would like to have that all data which belong to a cluster are close to each other according to this metric, which is just the sum of the difference between the vectors. And all the vectors within the same cluster are close to each other and close to the centroid to the center of this cluster, and while are potentially more distant from the centers of the other clusters. This might seem a bit difficult to do, but there is a simple algorithm which does this iteratively, and actually in the right setting allows you to identify these clusters very fast and very nicely. So the algorithm, it's called k-means, and works in the following way. You random pick k centers, so k vectors within your data. You assign each element to the cluster which is the closest center, and you compute the new center for that cluster just as average of the points within that clusters. Then you do again the assignment step. So you have moved your center, and you try you assign the data points to each cluster based on which center they are more close to. In practice, we can see very easily what's going on. So I have here plotted 3 main clusters. So if you look at the data intuitively, because it's 2-dimensional and they are very well-defined clusters, you can immediately spot that there are 3 main groups, right? And you would like to be able to, you would like that your k-means algorithm to identify these same groups automatically. The reason it's important to do this automatically is because if you have thousands of features, the automatic algorithm may still work, while it becomes impossible to just look at the data and see where the clusters are yourself. So, how does the algorithm work? As we said, the first step is just choose some random centers for each of the clusters. So we will choose to look for 3 clusters, and so we'll initialize 3 centers. So we have chosen 3 random points. We weren't particularly lucky because they ended up all in the same group, which is kind of a bad initialization. And as first step, we assign to each of the centroids, so to each of the clusters, all the points which are more close to this center than to the other centers. So all points which are in the green area will be assigned to this center. All points in the red to this center, and all points in the blue to that center up there. The next step is compute the new position of the centers just as average of all these data points. So you have many different vectors. For each position in the vector, you average across all the vectors belonging to that center. So this center here will move somewhere in the middle between this group and this group, probably closer to this one because there are more elements there. And the red will move somewhere in the middle between the groups of red points, and the blue will remain pretty much where it is. At this point, we do, again, the assignment step. So all these points get assigned to blue, all those points get assigned to green, and all those points get assigned to red. And basically, you can already see we have identified all the points. Because once we do compute again the barycenter, all clusters are basically unchanged, and it's very fast. In just a few steps, identified all the relevant clusters. Where is the catch? There are many catches, but one thing we did was we chose to look for 3 clusters. And we knew that there were 3 clusters, so that was, in a way, kind of cheating. What happens if you kind of choose the wrong number of clusters? So let's see, for example, that we choose to have 5 clusters at the beginning. So if you run the same algorithm, you will have these centroids here, which fall in the same cluster, and which have basically nowhere else to go, will start fighting for the points within that little group. And you will have much slower convergence, because they are slowly stealing 1 or 2 points from each other. And you will have totally arbitrary distinctions within these groups. So this has identified correctly a cluster, but here this division in 2 of this cluster is totally random. It's just dependent on the initialization. There is nothing in the data that says that this point is actually different from here. So you see that the problem of choosing the right number of clusters can have a big impact on the performance of your algorithm. So one way you can deal with this problem is to start with very few clusters. So you start with 1 cluster, 2 clusters, and you compute the sum of the square distance between each data point and the cluster you have assigned that data point to. And you will see that while you increase the number of clusters, obviously the sum of distances gets lower. But at a certain point, increasing more and more clusters will actually not result in significant improvement in terms of the sum of the square distance. And this is the point which is usually chosen as the right number of clusters. So because as you go on, you will obviously reduce it more and more, but you're probably not identifying some actual structure in the data. You're just splitting your clusters in smaller and smaller bits. So this addresses one problem, which is how do we select how many clusters that we are interested in. However, it's not the only problem of k-means. One thing we were saying is that we just choose to assign the data points to the closest point. So the way we assign points is basically inherently symmetrical. There is some spherical and rotational symmetry in the way we assign points to clusters. So if our data doesn't reflect this property, so if the clusters we see in our data is not fundamentally spherical, like in this example, we have data arranged in a big circle, some small groups which k-means could probably identify, another group here which has a random shape. K-means will basically fail to converge. So I mean, it will converge to a random. This is I ran k-means on this specific data set, and you see that it didn't identify any reasonable substructure in your data. So this is a second important limitation of k-means. Another important limitation is that it doesn't deal well if the clusters have different densities. So if your data, if you have some clusters which are very close to each other, very tight within the cluster, and some clusters which are very far from each other, like in this example, the best way to minimize the distance between the data point and this cluster you assign him to is actually to have multiple clusters in the low density cluster and potentially group other clusters just because they are nearby. And this is also a thing which is actually not extracting the right information, the useful information from the data. So for this basic algorithm, which is good because it's very fast, you can implement it very easily, and it gives you a first understanding of your data, we have quite a few limitations. So besides what we said, so how it deals with the data with different densities and data which is not spherical, there are also other problems. For example, it's not if your data is not continuous, so if your variables are not continuous values but they are discrete, it's not immediate how to adapt it to work. There are variants which try to take care of this, but it is a problem. And also, a thing you will often find in your data, in real-world data, is that many of the variables may be missing. So just because the data is corrupted, because the data is not available for some reason, maybe the person has not answered, if it's a questionnaire. And in this case, there is no way to deal with missing variables. So missing variables are a big problem in general in machine learning, because one thing you could do is just to assign a special value to it, but then it's not necessarily easy to represent this value, because if your value can assume any value between minus infinite and plus infinite, there is no value which is special. And if also, another thing you might do is assign the most common or the average value for that variable. But this can work, but has a limitation on its own, because, for example, in false, people might answer or not answer in different, the amount of people that don't answer may be different in different parties. So if you just split the missing votes among the parties evenly, you will actually bias your results in one or another direction. So this is a problem which is very difficult to deal with in k-means. And so different types of algorithms which use probability theory and probabilistic modeling can deal with this, but this is certainly a limitation for k-means.
You know the last slide, can you explain, did the k-means actually change the clusters? Did k-means cause the right-hand side, or
yeah, this is the data.
Yeah.
And this is how, and this is the splitting in red, blue, and green, which a person would say is clear that this is a cluster and these are other clusters.
Yeah.
This is how the k-means return gave me the results. So instead of identifying the three clusters, actually minimize the sum of squared distances by putting as many points as possible here and just sharing those two clusters. So, other limitations is that each data point must be assigned to some cluster. So if you have your data which is noisy, and there is some single data point which is totally out of the region, it's totally wrong, he will be assigned to some cluster, and when you compute the position of the centroid of the cluster, that cluster will be perturbed in a random direction, just because there is some random noisy data. And also another feature is that the convergence of the algorithm is not guaranteed to the global optima. So if you run the same algorithm with different initialization, you might end up with different final results. This is not really a problem because it's a very fast algorithm, so you can potentially run the same experiment multiple times and select the best results. And in other problems which you can address is that it's not scale invariant. So if one of the variables of your vector has a bigger scale, it will weight more in your sum of squared distances. But also this you can address, because you can normalize all your inputs in order to be, for example, in a region between 0 and 1, or some other bounded region, and then you can easily address at least this problem. So, if you have succeeded in downloading the code, you can run this file, blobs k-means. You just need to navigate to your folder within the terminal and run this command. And this is basically aimed at just give you some understanding of how k-means react with different types of data sets. So, for example, how does it perform if the data is not spherical? You will see, you can do some experiments, and you will see that it will usually fail to address these pre-clusters. For example, they are all split, and each of them is split between multiple clusters, because there is no because the data is not symmetric and spherical. K-means cannot really deal with it. And this is the example for the problem I said about data having different densities. And this is another example which maybe is so addresses the problem of having clusters which have different number of samples within. So this is less problematic because very often it will actually converge to the right point. But also here, the number of initialization which you might need to run. So if you run the same script multiple times, you might see as sometimes this will also converge to the right result. So this first example, just run it and try to experiment maybe different number of clusters and this kind of stuff and see how it works. There is nothing to complete on this example. Well, there will be a small exercise to do in the next one. So if some of you now fail to run it, is a good moment to ask if you have any problem with that. When you run it, it should take a couple of seconds, maybe 10, 20 seconds, so don't get anxious if it doesn't pop up immediately.
Is it in Python 2?
You should, it was supposed for Python 3, but it should have other distance functions that tries to account for what you are saying. So for example, you could try to penalize more if there is a distance in some direction, and or penalize, give more weight to one of the variable if you think it's more important. And all of this is, you can change this function as you want. So the answer is yes. It's not always obvious how to do it. So if your data has 2, 3 variables, it's easy. If you have 10,000 variables, even get to understand what the shape is complicated. So, but yeah, the answer is yes. It's actually something people will do. So I will. The random state variable just assigns the state to the random number generator, which is the one who creates the different initialization. So the aim is that if you set the random state, then every time you run the script, you will get the same random initialization. But if you run, and it's just a way to make it a bit more deterministic. And so what's going on in the code, I'll just run you through fast, is that here I'm just using the data. I'm just creating these blobs, which are random. And here I'm using k-means. K-means is the class within scikit-learn, which already implements all the algorithms. And you just need to specify the number of clusters and some random initialization. And this fit predict allows you both to fit the data and to try to give some assignment into clusters. So each of the data points will get in it y predict a different ID, a different number, which specifies which cluster he has been assigned to. And this is just a very simple way of using matplotlib to print the result. So this first part of the code generates this example down here. So I had specified 4 clusters as k, and therefore I've got this weird splitting of this data here. So this second part here instead tries to make an example to illustrate how things behave when you have the data which is not spherical. So this specifies how the data is along in different directions. So how is more or less symmetric in the different directions. And again, you can use, once the data is generated, it's just a simple way of generating some random data. You're using the same class, specifying the number of cluster, fit predict, and gives you an assignment of each of the data points to a different clusters. So if you then print them, and you specify as color the label, he will assign one random color to each of the clusters. So each of the data points will appear here with a different color depending on the cluster he has been specified. And sorry, this was for the different different densities. So anisotropic data. Then the non-spherical data. Well, this one here is just the different densities of the data. So this script here produces these results. And you see that the process is very simple, basically. Once you have generated your data, which in general will not be generated by you, will be loaded from some data set, from whatever you want to analyze, scikit-learn gives you a really simple tool to get you a first understanding of what is going on into your data. So the second example I wanted you to do now is to use the same basic simple algorithms, so simple function calls. You will just have to write like 2-3 lines to use k-means to perform compression. So the code is in color quantization. There are two versions of it, exercise and solutions. In the solutions you find the few lines of code which are identified with a to-do in the exercise field for you. But I would suggest you to try to make it work on its own. So what it does is basically it takes an image. It builds the data set you are analyzing by taking each pixel. Each pixel in an image is identified by 3 numbers. So it's the red, green, and blue channel, and takes all the pixels of the image and applies k-means on this data set. The idea is to identify which colors which are more frequent, and therefore compress your data by, instead of saving for each pixel all 3 dimensions, just store for each pixel one identifier which specifies which cluster he is assigned to. And then when you reconstruct the image, you just use the centroid of that cluster as new pixel. You will see that you can actually reduce hugely the number of colors while preserving a reasonable performance. So I can show you here. So the image is just this small image here. Here we are using all 3 channels to represent each pixel. So each pixel can assume one between 96,000 colors. So it's quite a rich representation. On the right, we are using just 64 colors. So each pixel can only belong to one of 64 clusters. And you actually see that this is enough to reconstruct basically the entire image, because most of the data there tends to cluster around certain specific colors. So you get huge compression just by applying a very simple and straightforward and fast algorithm. So if you open the corresponding file in your repository, there is the version called exercise, and there are 3 to-dos which are basically required to just apply the k-means of class of scikit-learn as it is done in the previous example. And once you have done that, it reconstructs the image for you. So at the beginning, so you will have to start here from initialize k-means k-clusters. The part before this basically loads an image, takes the image, which is now each pixel is represented for each channel with a number between 0 and 255. It transforms it just fall in the range between 0 and 1. It builds a data set by taking each of the pixel and making that a different row, which has 3 values, one for each color, and builds this big data set. And then what you have to do is just initialize the k-means class in scikit-learn, specifying the number of clusters you want to try to compress your image with. And then you take a subset of that data set to be faster. You apply k-means, and you should be able to then reconstruct the image just from that small amount of data. In the imports, there is scikit-learn datasets, which includes a lot of data, and including this image. If you have installed scikit-learn, scikit-learn comes with all the sort of data sets. So among them, there are these sample images to do simple.
I just have a question. So the command China equals to NP array. So that means that if I load a picture into an outside array, it automatically do a matrix with each point feature, right?
Exactly. Builds the matrices, which has 3 dimensions. Where the first dimension gives you the 3 channels. So it's the 3 RGB representation. It's one color, which is represented by 3 values: the R channel, the P channel, and the Q channel. So for each data point, you are assigned the three-dimensional representation in RGB format. So that is enough to represent is how your image is stored in the first place. Simply, it's instead of your image assuming values, any value between 0 and 1, it will assume only certain specific values, those which correspond to the different centroid. So we'll just choose the closest among the centroid, and this will have a representation this way. Which is the average point between those which have been assigned to that cluster. And that is your color along the 3 dimensions. Initialize k-means with k-clusters is just using the k-means class, which is imported at the beginning, and specifying the number of clusters. So that should be done easily. The second step is to take your dataset, which has already been structured here, just take a subset of it, because otherwise it becomes a bit slow, and just use this class to fit the data and predict and compute the clusters. If you have doubts on how that can be done, there is the example, the previous example, which does uses the same class and calls fit and predict to do the same stuff. The second step was to apply clustering to your data. So this can be done using the simple interface that the k-means class offers you. So you just take the k-means object, which you have initialized, specifying how many clusters, and call fit and passing the data you want to cluster. In order to make the things faster, what I did is I shuffled the pixels and just took the first 1,000, just a subset of it. And the interesting thing is that even with just using a subset of the data and just using 60 clusters, you get a pretty good reconstruction of the entire image. So this is just, it can be quite robust. The last step you have to do is once you have fit your model, so you have done your clustering, is use it to use the predict function to predict each pixel to what cluster it belongs, and then you can feed that to the subsequent part of the code, which will actually reconstruct it. This is done very, very easily using the predict function. So you take again your data, you use it to predict, and you get the label for each of the data points. Then using just this information, the code reconstructs the images, and you get this nice result. So with only using a fraction of the possible colors, you actually get a pretty good reconstruction of the entire image. So given that we are a bit strict with time, I would now go on. But I would advise you to, maybe when you have time, just look again into the code and to the details of how this is done. So, we said that k-means clustering has quite a few limitations. We said that it cannot really deal well with non-spherical clusters, that with different densities. It has quite a few problems which can make its use in practice quite limiting. So the second idea I wanted to present is just to show that if you change what you mean by things being similar, the way you define belonging to a same cluster, you can get a totally different algorithm which will perform well in a variety of different situations. So this idea is spectral clustering. Under spectral clustering, there is actually a family of countless algorithms. I will just show you a very simple and basic version of it. So spectral clustering attempts to deal with the problem of non-spherical clusters. So instead of using the sum of square distance, which is an intrinsically symmetric metric to evaluate how two things are similar, it uses a probabilistic model to basically define as clusters a group of tightly connected elements. So 2 points which are far from each other, but are connected by many points all close to each other, will still be considered close and belonging to the same cluster. So is a totally different definition, which uses the connectivity within your data to get a more, to deal with cluster of totally arbitrary shapes. So if you have a data set like this one, for example, it's clear from a human perspective that there are two main patterns. There are two spirals which interleave, but these points are somehow all connected to each other, all in the same group. So if you use a definition based on points being close to each other, this point and this point will never be grouped together. If you use a new definition which makes points tightly connected being in the same cluster, then you will have a chance to actually cluster also data represented with such a weird structure. So let's take, for example, how do we define this more formally? So let's take this point. We could define as first thing a measure of how things are connected. So two things will be strongly connected if, in first instance, they are close. So the first thing you will construct is a graph of how close and how connected things are. So this data point here will be close to his neighbors in the gray area, but will be far from these points down there. And you will then create a dynamical model of how you could move along this data. So if you assume that that you have a high probability of moving, you can from one point jump to any other point in your data set. But you have a very high probability of jumping to close points. But you have a very low probability to jumping to far distant points. So jumping from here to here will be very difficult, and jumping from here to here very easy. So let's assume you have this dynamic of the system. And you start in a random point, for example this one. If you look a few steps ahead, you will have a certain probability of being in any other point of the dataset. However, points which are close to the beginning, but also that are close to other points which were close before, so any point along this sequence of tightly connected points, will have a reasonable probability of you being in that state, because there is a sequence of high probability transitions which can lead you to any of the points on the same connected component of the state. Instead, the points that are in a different, non-totally disconnected subset of your data will have very low probability of ending up in that state. So, if you start here, you will have, and you represent, you assign to each of your data points a vector which represents the probability of ending up in any of the other data points after a certain number of steps. You will have that, for example, the representation of the red point will have high values for points which are on the same connected components and low values for the points which are on the other connected components. This gives you a better representation because you have a new dataset, which is also a collection of spectrums, but in which points which are on the same connected components are actually close to each other in the usual sum of squared distance, and points which are in non-connected components are actually far. So you have changed your representation of the data, and now it's data which you can easily cluster, for example, using k-means. So let's go a bit more into the details. So we said we want to have a measure of how distant things are. You can represent this with a big matrix. So you have a big matrix which has a measure of distance between points. And this measure uses an exponential. So this means that points which are farther from each other will have a very low matrix and low distance, while points which are close to each other will still preserve a reasonable metric. So the exponential makes the effect much more pronounced. So if you are twice as distant, you will not have half of the value, you will have a much smaller value. Then you can define your dynamic of the system just using those distances and defining the probability of going from a point I to another point J as proportional to the distance measured with this exponential metric. Then, now you need, for each point, to generate a new representation. So this new representation, which gives you the probability of, after a certain number of steps, of being on any other of the points of the dataset. If you represent your vector with what is called one-hot encoding, what hot encoding means that you have as many points, as many elements in the vector as the number of data points, and you have one that identifies which data point you're considering, and all the others are zeros. And you multiply this repeatedly for the transition matrix. This simple rule will give you this distribution of probability of being in any of the other points after k steps, where k is the number of steps into the future you look, and is the number of times you will have to multiply this simple matrix which you have created. Once you have generated for each point this new representation, you can just cluster it using k-means, because this data set will now have many very closely, approximately spherical clusters, which is the perfect setting for k-means. So basically, what is the idea underlying this? What I want to stress is that beside the detail of how we have defined the distances, how we have defined the dynamic of the system, the important thing we have done is we have transformed our data set in a new way, in a new form, which is suitable for the problem we're trying to face. And this is a powerful idea that goes beyond clustering. So the second subset of unsupervised learning I wanted to talk about deals exactly with this kind of problems, finding better representations. Okay? And this is what's called feature extraction. So feature extraction tries to automatize this process and is a collection of different algorithms which define better representation, where better is according to some sort of metric. So depending on the domain, again, you will have different algorithms which extract you the better representation for the problem you're trying to face. If you're trying to do clustering and you are interested in closely connected components, the spectral cluster algorithm is a feature extraction algorithm, if you want, that generates a representation which is good for clustering. But if you're interested in doing supervised learning, then maybe a different kind of algorithm will actually generate better features. So this is a thing which is actually crucial in supervised learning. So very often, rather than just choosing a fancier model to do the supervised part, it is really important that you actually manage to get good features. So this can be done by hand. So if you have a very good knowledge of the domain, you are trying to predict the outcome of football matches and you are a very big expert, you can try to devise some metrics which you build on your own and you know how they work and which identify what you think are the key elements to predict the outcome of a match. Please.
Yeah, in the spectral clustering thing, did you multiply the transition matrix by the similarity matrix to get to a distribution, or are you trying to get to different vectors for each point?
No, I get this distance matrix from which I derive this transition matrix B. And then I use this to get the distribution of probability over a data point. So starting on point X, this computation gives me how likely I am to be in any of the other data points after k steps. So speaking of feature extraction, in supervised learning we said if you have some knowledge of your domain, you can devise rules on your own which identify what you think are the relevant features of your data. But in many cases it's not easy to do it. So you're speaking of images or multimedia data, or just you have so many variables you cannot really take them all into account on your own. Automatizing the process can yield better results in a fraction of the time. So the outcome of the feature extraction algorithm is again a mapping that maps your data into some other vector, which in most cases you're interested in being smaller than the original vector. So you will have less elements in your vector, but you will be preserving the important information for you. So just as a review, a vector is an ordered sequence of elements. And you can think as each location in the vector as measuring how much that vector extends in one direction, okay? In one of k orthogonal directions. So if you have vector x of 2 elements, one element will measure how far you go along this axis and how far you go along the other axis of the second element. And you can generalize this idea across the dimensions. So you can have a vector with 3, 4, 5. You can still think of it as extending along different factors of variation of your data. This set of directions you're considering is what is called the reference system. One of the most famous feature extraction algorithms is based on this, on the idea of a reference system. So what PCA does, PCA stands for Principal Component Analysis, is select a new coordinate system, which is still a set of orthogonal directions, in which each of the new attributes you're considering is a linear combination of the previous element of the vector, and which is somehow better. In which sense is better? PCA selects the reference system that preserve as much information in the fewer number of dimensions which you want to preserve, and does this by minimizing the reconstruction error. So it selects the reference system with a given number k of dimension, where k is smaller than the original number of dimensions, which minimizes the reconstruction error. So it allows you to reconstruct, using just a simple linear transformation, the original data as well as possible. Okay, how can you do this? If you do all the math, turns out that the one way you can do it is selecting the directions where there is more variation. So if your data is arranged like this, is basically arranged along the line in your plane, you can see that actually if you consider all possible alternative reference systems of 2 dimensions, there is one which actually contains all the variation of the data. So all data actually is aligned along this line. So if you choose, instead of this reference system, a new reference system with which one of the axes is aligned along this line, you can actually ignore the second representation and preserve all the information in your data. So PCA will choose exactly this new reference system as new reference for your data, and this will allow you to basically have half of the number of attributes to store. In general, obviously, you will not have all data along one line, so what you can think PCA of doing is evaluating how much the data is distributed along the different direction, then choosing the direction which has the maximum amount of variation, and choosing that as first component. Then, among all orthogonal directions to that one, considers the ones which has the maximum direction. So this has the maximum variation along this axis, and this has another smaller amount of variation, and you could have many more dimensions, obviously, in your data, and he will increasingly add directions in its reference systems, choosing the one among the ones orthogonal to all the previous ones, which preserves the most amount of information about your data. So this is an interesting application which was published in 2008 on Nature. So they took basically all the genetic, big data set of genetic information about people in Europe, and they applied PCA to, the genetic description of a person is obviously a hugely dimensional data. You have thousands of directions. If you take the 2 directions, which have maximum amount of variation, and you compute them as some combination of all these different variables, you actually get 2 directions which reflect the distribution of people in Europe geographically. Italian are distributed along this area, Spanish people are down on the top left, and all countries are actually distributed according to geography. And this makes sense because the migration and the amount of sharing of the genes among populations is obviously proportional to how close and how strongly these populations interact. So you have that from this totally incomprehensible data, if you try to identify the 2 directions which are most relevant, you actually get what you would expect to be. So geographical information is the main factor of what captures the most amount of information about your genetical data. And this is another application of PCA. So if you try to apply PCA to a data set of faces, what you will see is that you get sort of templates of faces, where each person is somehow a combination of these. So obviously for faces you will not have just these few faces, you'll have many more templates, which somehow you can mix together to generate all the faces in the dataset. So you'll have some faces with beards, some without, some with smiling, some are not smiling, different shapes of the head, different features of the face, which you can use and recombine in different ways to generate your data. So, in many of these algorithms, like we said in k-means, there are anchor parameters, which are values which you are not learned from data. You need to set them beforehand to initialize your algorithm. So in k-means, we had that you had to specify how many clusters you were looking for. In this case, you have to specify how many components you want to keep. So you want a new reference system which has a certain amount of directions, and you want only to have a certain number of them, because you would like to keep as much information as you can while compressing your data. And one way you can do that is by measuring explicitly the reconstruction error. So what we said is that what PCA aims to do is minimize this reconstruction error. So preserve as much information as possible in the minimum amount of variables. This is the MINS dataset, so it's a dataset of handwritten digits. The full image has 784 pixels. And you can see how the reconstructed image becomes worse and worse as fewer components you take. But at the same time, you can see that you can actually remove a lot of dimensions without losing in performance. So going from 784 to 394, so almost half of the data, doesn't really makes big difference in terms of the image that you can reconstruct from the data. And this means that you can have a huge compression without losing accuracy if you want to train a system that learns to recognize which number is written. And you can actually go down probably to 50 components and you can still recognize the number. Maybe with 100 is a bit better because it's a bit, more neat and defined. And you can therefore use your reconstruction error to guide you in how many components to use. So this is a simple example you can find in your folder, MINS PCA KNN. This uses PCA as pre-processing step. So we said that PCA can help you to build better representation, which allow you to perform better in or equally or better in your supervised learning tasks. So here, as classifier, I chose KNN. KNN is a very simple algorithm. Basically, takes all the image in the training set, and when you give him a new image, he just computes the distance between the new image and all the images in your dataset, and returns the classification of the most similar image. So it's the most basic algorithm you can think of. And I applied it with to data which had been compressed using PCA at different levels. You can see that at the beginning, actually adding components results in a big increase in performance. But actually at a certain point, adding components will see the performance going down. So you are using, in theory, more data, a better image, and your performance actually goes down. The reason is that what you're doing is you are fighting overfitting. So if you are using the full representation, your algorithm might use very little, very subtle things, nosy things in your data to try to predict a new variable. By abstracting just the very important features of your image, you can actually avoid this from happening and result in better performance on the test set. You can try this out, and just by running the script is already complete.
Does PCA ever help with unsupervised tasks?
Sorry?
Does PCA ever help unsupervised learning?
Well, PCA is unsupervised learning. So you are taking your data, and irrespectively of what you want to predict, you are generating a new representation. So this is a form of unsupervised learning. Then you could use it as pre-processing step of another unsupervised learning task. For example, you could first compute your PCA representation and then apply a clustering algorithm. And also that would result often in improved performance.
Does it actually help? Because unsupervised isn't it the case you want as many features as possible?
Not necessarily, no, because if you have many features, you will often have a lot of noise, and you will find matches among data which are due to just random chance, while abstracting from your data only the most important features can help you also for a clustering problem or other unsupervised learning tasks. So if you look at the code in this simple script which I showed you the output from, you can see that actually doing a reasonable complex task, such as finding all this best reference system among all possible inner transformation of it, can actually be done in quite a few lines of code. So most of the code is actually loading the data, splitting it in training and test set, Then initializing your classifier, which is the k-nearest neighbor classifier with the number of neighbors you consider just equal to 1, so the most basic thing. And then here I'm considering 10 different values of the number of components. And here I just do a loop, and basically PCA amounts to this very small code. So I initialize a PCA class from scikit-learn. I fit the data, and this selects the new reference system. Then I transform the training data, and I transform the test data. Then I use the classifier. I train the classifier on the train data, on the train transform data, and I use it to predict the transformed test data. I measure the accuracy, and I plot it. The result will be the one I showed you before. So you will have that the performance will increase at the beginning, but actually start going down as you increase the number of components, because you start reintroducing into your data random noise and things which are not actually relevant for the classification problem. So one thing you could try to do, although we are a bit short on time, but you could try on your own if you're interested, is combine PCA with better algorithms. So you see that now we go up to about 65% accuracy, which is not super excellent. But we could definitely do better. So if you use PCA and you combine it with the random forests or with logistic regression, there are countless algorithms which you can apply. And by decomposing the problem of learning representations from learning a good classifier, you can combine them in any possible way. So you can use any possible feature extraction algorithm with any possible classification algorithm and combine them and see how what is the best choice. What we will talk about next time is neural networks. One of the powerful features of neural networks is that they explicitly combine these two steps in one. So what the neural networks, especially deep neural networks, which are now very common in image recognition problems and this kind of stuff, is use the lower layers of the networks to build these abstractions, these new representations. And then the top layers of the network will try to combine this representation into actual performing classification and regression. So the neural networks will combine unsupervised learning in a way and supervised learning. I mean, will combine feature extraction with supervised learning and perform both at the same time. Another script that you can find will just produce the reconstructed image for the different amount of components which you have retained with PCA. And the final example I would like to try is the eigenfaces exercise. Again, there is a solution, and basically computes, given a data set of faces, the principal components. So these template faces you can use to combine to generate with the reasonable approximation any face in the data set. And you can see how they vary with the number of components. And it's interesting to see which features are extracted. So how they smile, posture, and different subtle features which are identified into the different templates. So the code is in the eigenfaces exercise.py, and there are just a few lines that I would like you to try to fill in. You can use the previous example, the mince PCA KNN, to see how PCA is performed, how you can do it very easily with scikit-learn. I will give you a few minutes and I'll show you this. Use PCA to fit the data. This takes your data X and finds the best reference system for it. You can access the components by using the attribute components underscore of the PCA class. Once you have fit the data, this will be set to the components which have been identified. And then the plotting just requires you to reshape in the original shape of the image your principal components and plot them. This will give you these template faces which have some have beards or different shapes of the faces on the head, and you can print many more of them and have a look at how they look like. And yeah, this is basically it for today. So next time we'll be talking about how we can use neural networks to perform both these things, so feature extraction and supervised learning at the same time.